Let's begin. Exercise 16B. Complex numbers. We're now moving on to multiplication and division of complex numbers. Okay, so we learned how to add yesterday. We knew what complex numbers were. Today we're learning how to multiply and divide and solve. Because obviously we can add, subtract, multiply and divide. Then you can solve, right? So let's go. Multiplication, division of complex numbers. It's very similar to, because you can add, but remember when you're adding all the real values and you're adding all the imaginary values together. So reals with real, imaginary with imaginary. That means that when you do the distributive law, you're also doing, when you're adding them, you're adding reals and imaginaries together. Okay, so let's take an example. They say here that if you multiply Z1 and Z2, you will multiply them, and the way they grouped it looks weird and strange, but really, it's still your distributive law, your expansion of two brackets, exactly the same way, except the final part is you add the reals with the reals and imaginary with imaginary. So let's take this example here. Z1 is 3 minus 2i, so I'm going to write it down. 3 minus 2i multiplied with 1 plus I. Okay, so this is my multiplication. And that's exactly the same as how you've done it with real numbers, only now you've got imaginary numbers in there. Okay, the only difference is you can't add all the real numbers together. They are separate. Imaginary numbers and real numbers are different number systems. Okay, so if we would expand this, we'll do the same thing. We say 3 times the 1, 3, and then 3 times the I. I've got 3 groups of I, so 3i, and then I've got negative 2i times 1, so I've got minus 2i's, and then negative 2i times I gives me negative 2i squared. Okay, now from here, obviously the i's, we've got 3 groups of I and negative 2 groups of I over here. So in terms of the number of imaginary numbers I have so far, I've got 3 minus 2, which makes sense that I have 1 I. Okay, so these two give you 1 I. That makes sense. Now in terms of a real value, this is a 3. But over here we've got I squared. Now from yesterday's definition, we know that I squared is equivalent to negative 1. I squared is equivalent to negative 1. So if that's equivalent to negative 1, we can say that negative 2 times negative 1 gives me a positive 2. So overall, instead of writing negative 2i squared, I can write that as positive 2. So if I now add my real values, this no longer has an I value. It's no longer an imaginary number. It is now positive real values 3 plus positive real values 2. That gives me a total of real values 5. Okay, so Z1 times Z2 is equivalent to 5 real values, or 5 real values of Z is 5, and imaginary values is I, 1I. How do we feel about that? Was that easy? Okay, so real with real, imaginary with imaginary is what we're doing. Okay? Okay, I'm going to leave that there for a moment. And that's what this formula is trying to say. You're still doing A times B, A times C, A times D. It's just that ones will be grouped with the imaginary. So if you think about it over here, I'm just saying A times C becomes the real, but then A times DI becomes the imaginary. That's why AD is over here. Okay, that's why AD is in the imaginary. And then BI times C, that's your imaginary. That's why it's in the imaginary term. Okay, and then BI times DI, 2 i's make an I squared. That's why it becomes real, and BD comes here. Okay, that's all the formula is trying to say. All right, let's go to the next one. Now, along with understanding how to multiply, so if that's how you multiply, another thing to learn is what we call the conjugate, because that's going to be useful for division, okay, or finding the inverse. That's why we're learning how to multiply the conjugates now. So just reminding ourselves, what is the conjugate again? We learnt that back in year 9 when we learnt rational and irrational numbers, like surds, for example. What's a conjugate again? What's conjugate? No, what's a conjugate? What's a conjugate? William Mason? Perfect. If you remember back in year 9 when we first learnt surds, you have 1 over, let's say, root 2 plus 1, and they say they want the denominators to be rational. What you had to multiply to make this a rational denominator was not do this. Why can't you do that? What's wrong with it? You still get a surd on the bottom. So if you try to expand this, the issue to it is you still get a surd or irrational value in the denominator. So what they came up with was if you multiplied by what they call the conjugate, which we can use difference of perfect squares, this is the conjugate. Definition of conjugate is it only works for binomial, bi meaning 2 terms. So when you have an expansion of binomial and it's just a difference of a sign, they call it negation, the negation of a sign. Oh, the conjugate in English, I think it means like connection. Oh yeah? I don't know what it means there. All right. So, now that we understand what a conjugate means, that means that if you have a complex number, so remember Z represents a complex number, it's made up of A and B, imaginary values, then the conjugate of Z would be A minus BI. Does that make sense? Yeah? Okay, so when we say the conjugate, because again it's binomial, you have an equation where you have 2 terms, then the conjugate of that would be the negation of your second term. Okay, so it's exactly the same 2 terms, difference is the plus and the minus. So, that implies now that the conjugate of negative 4 plus 3i would be negative 4 minus 3i. See, the 2 terms are the same. I've got negative 4, I've got a 3i. The only difference between the 2 is a plus and minus. This is important because it leads to this idea. Oh, sorry. Yeah? So once you understand what a conjugate is, this will lead to the next idea. If you're multiplying them together, notice the bar that we're using. We use Z bar to indicate that's a conjugate. Okay, so Z times Z bar is like saying Z times the conjugate. Okay? So just notice this. This is a conjugate symbol. Okay? Now let's have a look at this page. I skipped some of the proofs, but I'm going to show you the proof as well. Here we say the modulus of a complex number, Z equals A plus BI, is denoted by mod of Z, right? And is given by this formula. And then they come out, once you've got that, they now say, if you take the complex number, Z, multiplied to its conjugate, apparently this is equivalent to the mod squared. Okay, so now this is where I want to show you. I want to show you 2 different things. I want you to understand what it means when we say mod of Z, and what's the purpose of this, and then how does these 2 link? Okay, because this will lead to Argand diagrams and understanding the difference between complex number systems and real number systems. Okay, so let's have a look at this. Z times Z conjugate. So let's say Z times Z conjugate. Where did I go? Here we go. Z, let's say Z was A plus BI. Then the conjugate of this would be A minus BI. Fair call? Okay. So in the multiplication of the 2, you would say then Z times Z bar is equal to A plus BI multiplied to A minus. bi. If we expand this out, this is what we're going to get. We're going to get a times a, which is a squared. We're going to get a times negative bi, which is minus bi, a. And then bi times positive a gives you plus abi. And then bi times negative bi gives you negative b squared, I squared. Okay, technically it's the difference of perfect squares. A squared and then minus b squared. Yeah, technically it's just that, but I'm just showing you the expansion using multiplication that you learnt before. Now what you can see is this becomes a squared, these two cancel out, and I squared is negative 1. So negative 1 times negative b squared now becomes positive b squared. Okay, so how do we feel with that? That makes sense so far? Yeah, I'm just using difference of perfect squares. Square the a term, square the b term. Okay, normally it's a minus, but because the I squared makes it a negative, double negatives make it positive. Okay? Now, this is what z times z z bar is. But then the question is, what is this talking about here? Mod of z. So they said that the modulus of a complex number is denoted by root of a squared plus b squared. If we take it a step further, what we're really trying to say is this. Because when we're talking about a complex number, in order to represent it, what you need to understand is complex numbers have an imaginary part. It has an imaginary number system that doesn't exist in our real value system. Okay? Because of that, if we were to sketch this, if we were to plot a point, a complex number, we wanted to visualize what it looked like, then this is what it would look like. We'd say the real values of z on the x-axis, okay, things that we know, versus the imaginary values of z that you don't know, okay, but that we made it up. So we say if it had to work, root of negative 1, root of any negative value, let's say we could make it work. This is all the number systems for imaginary values. Now when we say a, b, I, okay, so let's say, I'll give you an example. Let's say z was equal to 4 plus 3i. What this implies is you're saying I've got 4 as my real value. So 4 is my real value. And I've got 3 as my imaginary value. So my imaginary value has a system of 3. Therefore, I'm talking about this coordinate here. Okay? Now remember, this is different to your xy coordinates. They're not your xy plane, because x and y planes are real values. This is an imaginary system. This is a real value system. So, what does it mean when you're talking about 4 plus 3i? Okay? We can't tell much from it besides the only thing that we can tell, and with all these values, if I change this to negative 2, 3i, it only tells you dots around this system here, and it only tells you how far you are from the origin. That's the only information you get at the year 11 and year 12 method points. Not until you get to uni that you start exploring how that affects your answers. Okay, because really all you're actually doing is you're looking at how the distribution of this 4 plus 3i is actually talking about a vector. Okay, you're actually talking about the distance from your origin. So, when you're talking about the distance from an origin, mod of z is actually talking about, because that's the only information that's useful. How far is it from the origin? And this ends up being a circle, because you think about it, this distance will have the same distance around. Okay, so in order to find this distance, that's what modulus of z means. So when you say mod of z, that's what you're actually finding. Okay, so when you say z, z times the conjugate, in fact, it's equivalent to this squared. That's what you're actually doing. Okay, so how do you find the distance? This is a Pythagoras' theorem. You're just saying that's 3 units here for imaginary value, 3 squared, plus 4 squared, and square root that. That's why this is a squared plus b squared, square root of that. That's why that's called mod of z. Does that make sense? Okay, so mod of z is the distance of your coordinate from your origin. That is talking about how long it is. It's talking about the magnitude of your z values. That's what it's talking about. Okay, because remember with values in general, if I talked about 3, you have a magnitude. You know how large it is. Even if I said negative 3, you still have a magnitude. But when you say 4 plus 3i, how big is it? What's the magnitude? How do you figure out how large it is? That's what mod of z is for. See, mod of z tells you a particular value. It tells you how large it is. Whereas our number system, we never needed it. You see, if I asked you 3, you knew, oh yeah, that's a length of 3. It had a unit of 3. It's how big it is. And negative 3 is still the same amount. It's still the same largeness to it. It's just a different direction. But when you say 4 plus 3i, and I say, well, how big is that? There's no definition for it. There's no value to it. So how do you get a value? Mod of z. See, mod of z tells you how big it is. So you can now compare, if I gave you now z is equal to, let's say, 10 plus 12i, you can tell me which one has a larger value. Because if you found the mod of z of both of them, there is a difference between the two. Okay, because now you can visualize it in terms of the amount. You can visualize it as in terms of the amount of magnitude. That's why you find mod of z. Okay? So, having said all that, is all I'm trying to say. Z times z conjugate, which we proved before was a squared plus b squared. That's what it was. And we now know that if this is mod of z, which is the distance, which is how large it is, then the square of your mod is obviously the same thing as a squared plus b squared. Okay, so if I squared both sides, it makes sense. The squares and the square root cancels out, and I've got now a squared plus b squared. So they're just saying that definition is that idea. So when you multiply z to its conjugate, you're finding the magnitude. Okay? That's the idea. That's the idea. Yeah? Now, obviously, in today's exercise, I went a bit deeper to get you to understand what you're doing. But in today's exercise, all you're doing is learning to multiply them. Knowing the difference between z1 plus z2 conjugate versus z1 conjugate plus z2 conjugate. See the difference between the wording I'm saying? z1 plus z2 implies that you need to add these two first before you define the conjugate. Whereas z1 conjugate plus z2 conjugate, you need to find the conjugates first before you add them. Okay, so your notation matters as well. Yeah, so let's do the first example here. A, you do the second one, I'll do the first one. So here we go, z1 plus z2. Adding all the real values together, 2 plus a negative 1 gives me 1. And then negative 3i plus 2i gives me negative I. Okay, so that's z1 plus z2. Now I want to find the conjugate of that. So conjugate of z1 plus z2 will equal to 1 plus I. Okay? Versus z1 conjugate plus z2 conjugate. Well, z1 conjugate would be 2 plus 3i. And z conjugate 2 is negative 1 minus 2i. Negative 1 minus 2i. Now if I add these two together, because that's what they're asking, they're saying what is z1 conjugate plus z2 conjugate? This now gives me 2 minus 1, which is 1. And then 3i minus 2 is also now plus I. Now what I want you to see here is very key. My answer for z1 plus z2 conjugate individually is actually the same as z1 plus z2 all conjugate. See, they're both different ways, but they both have the same answers. Now, if you try the second one, you should find that this definition is true. Okay? This is the next definition, that if you added the conjugates separately, or you find the conjugates of them both, it'll come out the same. Either way. And it's the same for addition and multiplication. Not subtraction and not division, but for multiplication and addition, it is the same. Okay, so if you would do the second one, z1 times z2, all conjugate, versus z1 times z2 separately, should be the same answer. Okay, so that's what I'm trying to show you here. All right? We're almost there. Just one last skill set. So far, what have I talked about? I talked about conjugate. I talked about multiplication. And in this case here, I talked about two properties. I said that the modulus of a z is the same thing as z times the conjugate. And when you find the conjugate of z1 plus z2 individually or the conjugate together, it is the same. Same thing as multiplication and addition. Okay, so I know there's quite a bit to take in so far. The final part is putting them all together to solve and to find the inverse, or to find division. Okay, that's what the last part is. Are we all good? All right, here we go. Next one. So finally we get to the point. Division of the complex numbers. Now, if this is z, let z equal to a plus bi. So z is your complex number. We want to find another complex number such that the inverse, because if you can multiply, that means you can divide, right? And every time you want to find division, the first thing you have to find is the inverse. Because if you can multiply, you have to find the inverse of multiplication, which is why they call it multiplicative inverse. Now, what we're trying to find is, if z is a plus bi, we're trying to find an inverse, so right here, inverse, such that if you multiply together, it should give you 1. Now, in a logical standpoint, you can say this, if this is a plus bi, you can say multiply that to 1 over a plus bi, and that should equal to 1 on a logical basis. Yeah, because we know that if you got abi divided by abi, it has to be 1. Yeah? The problem is, what is 1 over abi if we want this in a complex number system? See, in a complex number, this should be written with a real value of z, an imaginary value of z. Right now, I don't have that. Right now, it's in a very funny form. This is not a complex form. Okay, it's a fractional complex form. So how do you change this? And I can give you the answer to it. The answer would just be this, but I want you to see why. So I want you to see how they got this. How they got this as your answer. Okay? What I want you to understand is this is our goal. We're trying to change this so that it becomes a complex number. Okay? So, how do we change this to a complex number? Let's take a step back and see how they got this answer here. So this is what we want. Let's take a step. 1 over a plus bi, just like what you did in year 9, you don't want irrational numbers. In our case, we don't want the denominators to be complex. Okay? So the only way to do that is what you learnt before, multiply this to its conjugate. So if I do that, let's multiply this to its conjugate. You have a minus bi over a minus bi. If you work this out, in the numerator you have a minus bi, which makes sense. A minus bi times 1. In your denominator, this is the difference of perfect squares. This is z times its z conjugate, which we knew the answer before was a squared plus b squared. And that's what they're saying here. Okay, so all they've done is they've changed a fractional complex by removing the denominator of having a complex value. This is now your complex. Now you can rewrite all this. You can say, oh, that actually is my complex value mod squared, and on the top, it's my conjugate of my z value. Okay, that's all they're trying to say. Okay, but the logic to it comes from here. We're just saying that in order for it to work, it had to be z, which is your complex number, times the inverse. We want it to equal to 1. So logically, a plus bi times 1 over a plus bi should give you 1, because it's a plus bi divided by a plus bi. The issue is this. This is not a complex value. Sometimes you can write your answer as this. It's a fractional complex, but we prefer this answer. Okay, it's just like surds. You can write 1 over root 3, but we prefer root 3 over 3. Okay? It's sort of like saying, if I asked you root 3, 1 on root 3, it's hard to figure out where you are in the spectrum. But to change that to a real value, this is the same thing as writing root 3 on 3, and that's much easier to figure out. So with a root 3, you can roughly estimate that's about 1 point something and divide that by 3. You get a visual image. Whereas this one's a bit funnier. Okay, it's the same thing with a complex. You've got a fractional complex and changing it to a more of a easier to read complex number. Okay. Anyways, that's pretty much it. In terms of skills, I taught you multiplication. I taught you the conjugate. And I taught you the inverse. Okay, so out of all these skills now, the next few questions allows you to solve, and that's what you're doing. Okay, so let's have a look at the next one. Here we go. Using the skills you've learned so far, I want you to solve this. Solve for z in the equation. You have 2 plus 3i times z is equivalent to -1 minus 2i. It's the same thing. Use all the skills you have. You have add, you have subtract, you have multiply, and you can now find the inverse as well, which is divide. I want you to find z for me. How do we find the value of z? So z is a complex number. The value. Find the value. Find the value of z. Using all the skills you've learned. So everything I taught you is just the skill. This is what you want to do now to apply. And that's what exercise 16B is about. It's about applying.
It's a triangle. So you can't divide complex numbers. You've got to only times the conjugate. To write it in a more preferred form.
Yeah.
Because or else if it's like z to the power -1, you could just write 1 on that number.
Yep.
But you have to times it by the conjugate.
Well, that's what I asked the other teachers, and they're unsure. But they did say to me that it depends on the question. So I sort of rationalize it as the idea of like rational numbers. I think it's like you can have your answer as 1 over √3, and you can leave your answer as that, unless the question specifically says rationalize all denominators. Then you have to do the conjugate. So in like the next example, you see that one there, they said find z's inverse.
With a real number.
Yeah, and technically I would normally have read that and just said, well, it's 1 over 2 minus 5i.
Yeah.
But because they said express with a real denominator, then I have to do the conjugate. But I guess I'm questioning, can you just
Leave it as 1 on 2 minus 5 if it doesn't say.
and that's what I asked the other teachers. They said, yeah, you probably could. I think just for the sake of this exercise, that's what we're doing. But here we go. Let's solve this. Z will equal to -1 minus 2i.
Chapter 1 is pretty much.
So like in this question here, for example, whoops, could I have just left it like that and just said z equals 2?
Yeah.
And I think it's because they said solve for z, and z is a complex number, and a complex number has a real value and has an imaginary value. So whilst I'm looking at this, I don't know what the real value is, and neither do I know what the imaginary value is either. Okay, so if I now times it by the conjugate, this now will give me -1 minus 2i times 2 minus 3i over, technically this will become just 4 plus 9.
Oh yeah, 13.
Plus 9, yeah, so it becomes 13. So the nice thing is now I can say it's a factor of 1 on 13 multiplied 2. Actually, I'll just do it more obviously so that people don't get confused. But -1 times the 2 will give me now that real value that I was looking for. And -1 times -3 gives me plus 3i, that's my imaginary. And this is now minus 4i, that's my imaginary. And lastly, -1 times -3 is positive 3, but remember the I squared's got to make it a negative, so it's going to be -3.
Oh, 6. Wait, what?
Is it -6? Whoops. Wait, what did I do? -1 times 2, -1 times... And then negative... Oh, yep, yeah, you're right, sorry. So it's probably -6, yeah. And so that now gives me minus 8 minus I on 13, which we don't write our answers like that because you can't tell the difference between the real and imaginary. It's better to write your answer as negative 8 on 13. So now that's my real, and then minus, I on 13. That's my imaginary value. Okay, so that's what Z would equal to. And that makes more sense than leaving your answer as that. See the difference between the two?
Yeah.
And so now I can talk about the conjugate in terms of, not the conjugate, the modulus. I can talk about how thick it is, how the magnitude of it. I can say how far it is. Whereas leaving your answer up here, you can't tell much from it.
You know, you said you wouldn't leave it as the second last thing, negative 8, negative I on 13.
Yeah.
Will I be able to leave it like that if it doesn't specify, like, in the following form?
Yeah. I think if the question doesn't say, I think this is fine to leave it as that. Yeah. But if normally it would... Actually, I don't even know if normally it would specify that. Because technically both of them are the same thing.
Yeah, they're the same.
Because technically you can even write it like this. You can even say it's like 1 on 13, negative I.
8 minus,
Yeah. And that's fine. That's a like saying that's your Z value, complex number, and then you're doing 1/13 of it. That makes sense. There's nothing wrong with that. So yeah, I think you'd leave your answers there. How do we go? Was that fine and easy? Yeah, because that's the main thing. That's all you had to do. That's all you had to learn for exercise 17B, 16B. No. Yeah, no. 3 exercises left.
What only?
I was thinking whether I want to combine complex and vectors together because they're both similar, or do I separate them too? I'm thinking more like keep them together. And then same thing with probability. You got sampling and distribution that stays on itself. So I think vectors and complex, I might put them together.
What's chapter sampling on?
Oh, I forgot.
Because it's not the same as method sampling, right?
It's slightly different.
Yeah. Because there's a new sampling on the methods course.
Oh. Yes, sampling's new in the methods course for year 12.
Yeah.
But I'm pretty sure the theory is very similar. There might just be slight difference. Yeah. I think the only difference might be some extra properties in your sampling.
For specials.
Yeah, for specials. But otherwise, the theory should be the same, like what a sample is, what a